I'm going to shift this resistance homework from Monday until, it's scheduled. It's just going to be later in the week. I'm going to shift it to Wednesday so that we've got some of that stuff that's already going on. Because we're going to start resistance today, but I wanted to make sure that you guys have time to get it done. So I'm going to go back here. So the resistance homework is going to be due on the 7th, and we've got some circuit problems homework that's due on the 14th. As you guys can guess, we're getting close to needing another test. So what I'm going to end up doing is this. You'll get another quiz next week so that you'll have a quiz over resistance and capacitance, because that quiz was electric fields. So we'll get that going. Then we will get that's the quiz in WebAssign. I will probably run a quiz through Blackboard next week, so it'll be multiple choice like we did with that other quiz on Blackboard. And then March the 12th, all right? March the 12th, which is a Monday, we're going to do a test. And that test will cover electric fields, will cover capacitance, will cover resistance. What will not be on the test, even though we are going to start it and we're going to start working it next week, and I'm going to explain why it won't be on the test, are the Kirchhoff law circuit problems, where you have multi-branched circuits. Those will not be included on that March 12th test. On March the 14th, what I will do is I will give you the take-home portion that deals with the circuits. And those circuits will be due that Monday when we come back from spring break. So you'll have all of spring break to work those circuit problems, and you'll understand why when I start showing you the circuit problems, why I give that one as a take-home. Because if you start down the wrong path during a test, you're just toast. They're not necessarily hard, they're just time-consuming. So you'll get that circuit, those circuit problems will be on the take-home portion, which is why the circuit homework is going to be due on the 14th. So I'm going to do the circuit problems. I haven't quite decided exactly how I'm going to do it as the take-home part, but I always do that one as a take-home portion. So the circuit problems themselves will be a take-home portion, but the rest of the material that we've been covering from a resistance point of view will be on the test on the 12th. So your test will be on March the 12th. So we're getting there.
It's over capacitors and resistors.
It's going to be electric fields, capacitors, resistors, everything that we've covered up from sound, except the broad circuit problems. And we haven't done one yet, so, but you'll see why all of a sudden I'll say, no, that's a take-home portion. Because I just don't feel like it's fair to try and do one of those on the classroom. So you've got this quiz that's due tonight, there'll be a quiz next week, and then there'll be the test on March the 12th. So that'll keep us going. No class March 16th, okay? No class March 16th, that's the Friday before spring break. So there won't be a class March 16th.
And we still have the test in the testing center. We can take the 14th through the 16th.
No, I'm going to do it different.
Okay.
I'm doing that different. Rather than trying to get it arranged for the testing center, we're going to do it in class on the 12th.
Oh, okay.
Yeah.
I was like,
So yeah, there won't be a test through the testing center. I was going to do that, but I'm not going to do it this way. I'm going to go ahead and give you the test on the 12th. That way it's in class, you get it done, get it over with, and then you'll have your take-home portion for the circuits I'll give it to you on the 14th. So that you'll have that part, and then you'll have until that following, the Monday we get back for that one. And I just haven't figured out how I'm going to do it yet, whether I'm going to do it through Blackboard, whether I'm going to do it through passing them out and turning in paper copy. I haven't figured that out yet. But that's how we'll end up doing that one. So it kind of gives you a heads up on things, and yeah, so I'm not worrying about going through the testing center. I've got too many things going through the poor testing center right now, and with their midterms, I thought, I probably ought to not do that to them.
good, because I really didn't want to take 2 tests.
So we got that one straight. Okay. So So I put this one up just before, so you guys had a chance. We're gonna do a couple, and then we're gonna start into resistance, do a couple of problems, see if it's coming through. But you got a DVD player that requires 350 milliamps at 6 volts, and we want to know what the power requirement is. So if I do that, remember power is going to equal I squared R, or V squared over R, or it's going to equal IV. So what we've got here is milliamps and volts. So I'm going to do the milliamps and volts one. So my power is just going to equal IV, and that's going to be my 350 times 10 to the minus 3 amps times my 6 volts, and that gives me 2.1 watts. And you can start to see now why why trying to do unit analysis now is kind of weird, because I've got volts in different units, I've got amps in different units, and I end up in watts. So you can still go back and do your unit analysis, but you kind of have to go back and look at it and kind of keep it straight. So that's kind of one of the types of problems that we get. I've got another problem. I've got a waffle iron, and the waffle iron is rated at 1,000 watts. When connected to 120 volts. So it's rated at 1,000 watts. When it's connected to 120 volts, we want to find the current and we want to find the resistance. Okay, we want to find the current and we want to find the resistance. So I can go back to my power equations again, which is I squared R, which is equal to V squared over R, which is equal to IV. I've been given power, this is P, and I've been given my voltage, which is V. So if I want to find current, that's just going to be power divided by voltage. So that's 1,000 watts divided by my voltage, which was 120 volts. And that gives me 8.3 amps. And then if I do the other one, I'm going to use power is equal to voltage squared divided by resistance. Resistance is equal to voltage squared divided by power. So now I get my 120 volts squared divided by my 1,000 watts. And that gives me 14.4 ohms. So even though we spent a lot of time doing forces and electric fields, but when we finally get down to volts and resistors, things simplify again. Things get a lot simpler and simplify again. So we've got a variety of different things. Oh, let's do this one, because this one's always fun. So I'm going to do this one before we start tackling into resistors. Okay, so I've got the difference in cost between an LED light bulb and a standard light bulb. And what we're going to do, so we want to look at LEDs, and I actually am also going to do compact fluorescence. Okay? So this is a standard, this is incandescent, this is compact fluorescent, this is an LED. And this cost was based before they started totally getting rid of the incandescents off the shelf, right? Because now if you try to go buy an incandescent lamp, it's a little different. But this is back when we were trying to make this first transition. And these costs for LEDs haven't changed that much, and they haven't changed that much for compact fluorescents, but your incandescents, the costs are now starting to change a little bit. So you want to make sure when you're looking at it. But historically, we refer to our typical 60-watt light bulb. And the 60 watt came from the fact from its power requirements. It didn't come from what it actually emitted in terms of light. And what we now look at is if you go out there, you'll see something called lumens, and that's the measure of your intensity of the light. Historically, you would look at a 40 watt bulb, you would look at a 60 watt bulb, you would look at a 100 watt bulb. But now we need to look at lumens, and what they would now tell you on the box is this is an equivalent to a 60, the lumens is equivalent to a 60 watt light bulb. So this is a measure of intensity, this is a measure of power. So if I go and I wanted to get the equivalent LED for a 60 watt light bulb, and the equivalent compact fluorescent for a 60 watt light bulb, this is what happens. If I go get a regular 60 watt light bulb, it was expected to have a lifetime of 1,200 hours. That was its expected lifetime before it would burn out. My LEDs, so I'm going to do LEDs, compact fluorescents, and then standard. The lifetime for an LED is predicted to be 50,000 hours. The lifetime for a compact fluorescent is predicted to be 10,000 hours, and our good old standard light bulb is expected to be 1,200 hours. The watts that were needed for these, for my LED, it's 10 watts. For my compact fluorescent, it's 14 watts. For my standard, it's 60 watts. So those are our 3 light bulbs. If I look at the cost of my light bulbs. An LED was currently running about $5.98. My compact fluorescence is about $1.67. And my incandescent, before they started getting hard to get, was about 75 cents. We're going to use a typical cost per kilowatt hour. Remember, that's an energy, and it's going to be 12 cents. We're going to use that 12-cent number for a typical cost of kilowatt hours. So what the question is what's the cost to run these light bulbs? Okay, so what's the cost to run the light bulbs? So we're going to do it for the lifetime of an LED. So the cost to run one LED, 50,000 hours, and this is going to be hours, and this is watts. Because if I multiply watts times hours, I get watt hours. And I'm going to actually divide by 1,000, so I'm going to get kilowatt hours. So I'm going to divide by 1,000 for my kilowatt hours. This gives me 500 kilowatt hours. So if I do that, I'm going to take my 500 times my 12 cents, and it's going to cost me $60 to operate. And then it cost me $5.98 to actually get my light bulb. So for 50,000 hours, the cost associated with an LED is $65.98 over the lifetime of my LED. That's how much it cost me to do it. So now if I'm going to do my compact fluorescent, I want to do 50,000 hours, but it only has 10,000, so I'm going to have to buy 5 compact fluorescents. I got 10,000 up here. It's going to be 14 watts. I got to divide by 1,000 to get my kilowatts. This tells me it gives me 700 kilowatt hours. I take my 700 times my 12 cents, and that gives me about $84 to operate. I have to now do 5 times my 1.67 compact fluorescents. And so this gives me a total cost of $92.35. So my LED is gonna cost me $65, my, or $66, my compact fluorescent is gonna cost me $92. To get 5,000 hours for my standard, I'm gonna have to do 42 of them at 1,200, and it's gonna be 60 watts, so I gotta divide by 1,000. This takes 3,024 kilowatt hours. If I multiply that times my 12 cents, so I'm gonna take that 3,024 times my 12 cents, gives me $362.88. $362.88. But I gotta buy 42 of them, so 42 times 75 cents, it ends up costing me a total of $394.38 to operate my incandescents. Which is one of the drivers for why they wanted us to move from incandescents to compact, or the compact fluorescents, or to the LEDs. So now the question is, why did it take people so long to go to LEDs?
Because they're a little bit more expensive on the shelf.
So the first thought is they're a little bit more expensive on the shelf. All right, I will tell you that I was a late adopter of LEDs, even though I've run this calculation for years. I could tell you that I knew I was giving up almost, $400 worth of stuff not to run an LED, even though I knew that in the long run it's going to be cheaper. And I certainly won't go to a compact fluorescent. I only use compact fluorescents in certain applications. And I still won't use compact fluorescents. Guys, got any thoughts over there, Enid? Why I would be a late adopter?
Psychological.
Psychological?
Change.
No, it's not related. There is an issue with change, but I'll tell you what it is. It's an actual physical issue with change. Others over there, you got any other ideas from the group? Okay, we'll talk about why. Compact fluorescents, what is one of the things that you notice if you go into a room and the fluorescence is starting to go away? You're starting to lose a fluorescent bulb. There's a flicker. People who are prone to migraines will pick up the flicker. And a compact fluorescent will have that flicker associated with it. So you'll actually see the flicker, or get a chance to see the flicker associated with a compact fluorescent. It's gonna flicker at the same rate as my AC current. So compact fluorescents will have a tendency to trigger migraines, will have a tendency to trigger things. So I don't like compact fluorescents because I pick up the flicker. And so to me, those are hard on me. Now the compact fluorescents are getting much better, so you don't have near the flicker that we used to with the old compact or the old fluorescent tubes. But compact fluorescents will have a flicker. So that's one thing that causes me a problem with compact fluorescents. The other problem with LEDs, up until about the last year or so, we didn't have a good white associated with the LED. So for those of us who read a lot, work a lot on paper, it was a color issue associated with the LED, not so much of a cost issue. So if I'm reading and I was using an LED light to do the reading with, I got tired. I got really, really tired, and because the color was a big issue. So it was a color issue that actually prevented a lot of people from moving to the LEDs until recently, because now they've fixed, or they've gotten the right combination so that we don't have near the color issue. And now since then, I've switched out a lot of my lights in my house to LEDs. And it was really associated with the color that we were getting more than anything else. So it's not as, there's actual physical reasons why people didn't want to switch over, even though we had the compact or the incandescent. There are still applications where people want incandescent because you want the warmth. Like if I'm using a lamp in my reptile tank, or I'm using a lamp associated with my fish tank, I want an incandescent because I want to get the heat off of my incandescent light versus trying to do it with an LED, because I'm not going to generate near that kind of a heat with an LED. So that's one of those fun things to look at for why we do things and why we look at pieces and go from there. All right, let's start resistance. Let's start looking at resistance. So what we have said so far is we start looking at we've drawn our circuits so that I have a circuit that has a capacitor in it and I have a battery, and we've talked about this battery here. That's the positive, this is the negative, and we can have the current flows from positive to negative even though we know it's electrons that are causing it to go that way. One of the things that we do know here, this gives us our voltage, and this gives us, if I'm actually looking at a circuit, so this time I'm going to do a circuit and I'm going to put my resistor in the circuit. We started talking about this, so there's my current's going to go that way, that once I flip the switch, I'm going to get current that goes through my circuit. The resistor, I can look at this very similar, so I'm going to kind of draw it just a little funky here. So here's my pump, and I've got water flowing through a pipe, and I'm going to cause a little restriction in the pipe. So I get a little narrow piece of the pipe. I can look at current just like looking at water going through the pipe. If I get this little restriction here, I'm going to get resistance to how the current is going to flow. And I can look at my battery just like looking at it from a pump. All right? Just like looking at it at a pump. So we can think of these systems, think about it like the flow of water through a system. And when we do that, my battery becomes my pump. And when we talk about that, they'll get something that they call electromotive force. It's not really a force, it's really electrical potential, but when they were trying to describe what was happening in my wires and in my systems, we talked about electromotive force and thinking about my battery as a charge pump. Essentially, that's what it's doing. It's thinking of my battery as a charge pump. My battery is putting charge into the system, just like my pump was putting water into the system. So they called this electromagnetic or electromotive force. It's not really a force. It's really a potential. And so we end up talking about an EMF. Okay? We end up talking about an EMF, and this EMF is the maximum possible voltage. That the battery can provide. So that's the maximum possible voltage that the battery can provide, will give me what we call the electromotive force. And right up until now, we haven't talked about real batteries. We haven't talked about things that when we go out and we get a battery and we buy it at the grocery store, we put a battery in our car. We haven't really talked about it too much. We just said whatever's on the label is what we get. That's not really the case, because I can't really get that to happen. But we also said resistance is a function of temperature. And if you think about your car, many of you went out this winter and tried to crank your car, and you got a then it finally cranked over, right? And then, or if you did it with a tractor, and then if you have a big truck, they talk about cold cranking amps on your battery, because my battery isn't perfect. My battery isn't perfect, and I have to worry about what's happening in my battery. And we already saw that resistance is a function of temperature, and I have things that are happening with respect to it. We also know that when my phone gets hot, my battery drains faster. On my cell phone, you know, your battery will drain faster when your phone gets hot. So we have that resistance as a function of temperature, so my battery isn't perfect. My battery isn't gonna be perfect. I'm gonna have different things that are happening with my battery. And so for a real battery, all right, for a real battery, I can't just say whatever's on the label. And my real battery, my change in potential is going to equal my electromotive force, which we're going to use that E for my electromotive force. And we already know based on Ohm's law that V is equal to IR, okay, that my voltage is equal to the current times the resistance. My change in potential associated with my voltage or my battery is going to be the electromotive force times whatever current is going through my battery times what we're going to use as little r, where this is known as the internal resistance of the battery. So that's going to be my internal resistance of the battery. So we use this little r to mean the internal resistance. We use this r to mean the resistance of the circuit. So I can draw a circuit that kind of looks like this. So now I'm going to draw a box here, and this is going to be my battery. And my battery can be written as our perfect battery plus a little tiny resistor, and that's this piece. And then my circuit can have a big resistance, a big resistor, just like that. So this has been resistance, this is going to be my current, this would be the maximum electromotive force minus my little r, where that's my little r. So that gives us our real battery. So what we're going to do is we're going to find the current in the circuit if the battery has an EMF of 12 volts and an internal resistance of 0.05 ohms and is connected to a 5 ohm resistor. So we've got a circuit that's going to look just like this, except now we're going to be told that this is 12 volts. This internal resistance is going to be 0.05 ohms, and this resistance is 5 ohms. And we want to know what the current is. So the first thing we have to do is find out what our real battery is going to put out. So we can go ahead and do that. My change in potential is going to be my 12 volts minus my current times my 0.05 ohms. And for the entire system, I've got my current times my resistance for the system. That's going to equal my 12 minus I 0.05 ohms. And that's going to be 5. So I get 5I is equal to 12 minus I 0.05. And now I just solve for I. Okay, now I just solve for I. So let's go ahead and do that. So I'm going to rewrite this. I've got 5I is equal to 12 minus 0.05I. So I get 5I plus 0.05I is equal to 12. Factor out my i's. I get 5 plus 05I is equal to 12. So I'm going to get I is equal to 12. 5 plus 05. And when I plug that in the calculator, I get 2.3 amps. So So let's draw this, because this looks like a car battery, right? So this really looks like my car battery, and this is the negative side, that's the plus side. If I take my voltmeter, so I'm going to put my little voltmeter in here, just like I did in lab, and I want to see what it's going to measure, what it's actually going to measure, what I actually measure is the change in potential is equal to the EMF minus 2.38 amps times my 0.05. That's going to be my 12 minus that. And when I put that amp meter on there, I'm going to get 11.88 volts. And so what happens to you in the wintertime, if your car needs a certain voltage, and because of this internal resistance that's going through the system, all of a sudden I don't get the required voltage and I can't start my car. So you'll get pieces that look like that. So now we can say what's the power delivered to our delivered to the resistor, and this is the 5 ohm resistor. Well, my power is just going to be my current squared times the resistance. We know it's 2.38 amps times my 5 ohms for my resistor, and that means I'm going to get 28.32 watts. So your first set of homework problems on the resistance after that last chapter on the yes, ma'am.
Never mind. He pulled the paper up already.
Okay. Okay. All right. So now we've got resistors and we've got current and we've got a lot of fun things. So let's set up a system. And I think you guys have all done capacitors and resistors and circuits in series. Did you guys do capacitors and circuits in series yet over there, Enid? Have you played with connecting them in series and in parallel? Or is that this week? It's this week. Okay. All right. So what I've got is I've got a battery, and now we've got it connected to 2 resistors, and these resistors are in series. Okay, so I've got resistor 1, I've got resistor 2. And when I set up my system, it turns out that when I get my current in here, that my current throughout the system is going to be the same. So the current that goes through I1 has got to equal the current that goes through I2. So those currents are the same. So if I look at my change in potential, my potential in this system is going to be I1 R1 plus I2 R2. And this is going to be the current in the systems times the resistance equivalent for my system. Well, if I1 has to equal I2, that all has to equal I. So this becomes I R1 plus I R2 is equal to I equivalent resistor. I can divide both sides by I, and I get the equivalent resistance is equal to R1 plus R2 for series. Remember, for capacitors, this was for when I was in parallel. And for capacitors, that was in series. Okay? So you gotta kind of keep them straight, because now, if I set up my system so that I'm in parallel, I set up my system so I'm in parallel, So that's my system that's in parallel. The change in potential has to equal the change in potential going through 1, which is equal to the change in potential going through 2. So if I use my water analogy and think about it, the current, when I go through each spot, has to sum up because they go the path of least resistance. So when I come to this spot here, I start out with current, and then I'm going to have that current break apart. It's going to possibly go through here, and it's possibly going to go through there. So my current is actually going to go through, and if I use my change in potential is equal to IR, good old Ohm's law, and I'm going to set this equal to current, so I'm going to get my current is equal to the change in potential over R. Okay, my current's going to equal the change in potential over R. My current becomes my change in potential over the R equivalent is equal to the change in potential at 1 over the resistance 1, and the change in potential at 2 over resistance 2, but these change in potentials have to be equal. So I get the change in potential over R1 plus the change in potential over R2. It's got to equal the change in potential over REQ. I can divide out those change in potentials, and I get 1 over REQ is equal to 1 over R1 plus 1 over R2. And that's when I'm in parallel. That's when I'm in parallel. So we're going to have similar types of problems looking at equivalent resistors as we had equivalent capacitors. So let's do one. It's going to take me a second to draw the circuit. So I will draw the circuit. So I'm going to start out with a battery. This one is going to be 100 ohms. This one is 200 ohms. This is 100 ohms. This one's 150 ohms. This one's 300 ohms. And this one's 100 ohms. And we have for parallel, we have 1 over REQ is equal to 1 over R1 plus 1 over R2. And for series, we get REQ is equal to R1 plus R2. So that kind of helps us remember which way we're going to go. And the way to work these problems is you pick a spot to start. So I'm going to do this right here, and I'm going to do this right here. So those are both in parallel. So I'm going to do 1 over REQ is equal to 1 over 300 plus 1 over 100. And when I do that, I get 1 plus 3 over 300, because I did my lowest common denominators, that fun stuff. So I end up with 4 over 300, and that's 1 over REQ. So if I get REQ, I get 300 divided by 4, and that equals 75. And that's in ohms. I'm going to do the same thing for the other one. 1 over REQ is equal to 1 over 200 plus 1 over 100 gives me 1 plus 2 over 200. Now I get REQ is going to be 200 divided by 3 gives me 6.67 ohms. So now I'm going to draw my circuit again to put these equivalent resistors in. So now I draw my circuit. This is still 100 ohms. This one is now 66.7 ohms. This one is still 150 ohms. This one is now 75 ohms. Now my REQ is just gonna add them up because they're all in series. So I'm gonna get my 100 plus my 66.7 plus my 150 plus my 75 gives me 391.7 ohms. So that's the equivalent resistance. Now, if I want to find the current that's going through here, I just use V is equal to IR, or I is equal to V divided by R, and now I got to give you this. I'm going to use 100 volts for grins and giggles. I'm going to use 100 volts. So I'm going to get 100 divided by my 391.7. Whatever that works out to be, and I think it's around 100, yeah, it's around 0.25 amps. So when you're studying for your test for March 12th, you are likely to have to calculate the equivalent resistance, and you're likely to have to calculate the equivalent capacity or capacitance of your circuits. So you're going to have to be using your 1 over REQs and your REQ and the one for capacitors. Remember, my capacitors are different. You're likely to have those kinds of problems on the test. The stuff we're about to start is the stuff that you're going to have separate. And I'm going to start that on Friday instead of starting it today. Give you a chance to let this stuff soak in a little bit, and then we'll start doing the rest of the crunching that we're going to start playing with the overall circuits. You guys good over there, Enid? All right. And we'll see you guys Friday. And I will be here Friday. Thank you, Beverly, for covering on Friday.